Hello there. If integration still feels like a puzzle of memorizing random formulas, you've come to the right place. That's because, at its core, integration isn't about memorization at all. It's about something much more fundamental and intuitive: reversing change. In this video, we'll explore how integration actually works, and by the end, you'll be able to see the big picture and tackle integration problems with confidence, not just recall. One of the main reasons many students struggle with integration isn't because the concepts are inherently difficult, but because they approach it the wrong way. Often, the first instinct is to try and memorize a huge list of formulas, like the one you might see on a cheat sheet. But trying to tackle integration as a pure memory game is a dead end. It leads to frustration and the feeling that calculus is just an arbitrary collection of rules. We'll show you a better way. So what's the big idea we should focus on instead? Let's start there. Let's make this our first learning objective. By the end of this first section, you will be able to explain the core relationship between integration and differentiation. In other words, you'll understand why integration is called the antiderivative. Think back to differentiation. When we took the derivative, we were essentially measuring the instantaneous rate of change of a function. We started with a function, and we created a new one that tells us its slope everywhere. Let's say we have our original function, which we can call f of x. Integration is the exact opposite process. If we're given the rate of change, f prime of x, we want to rewind that process and find the original function, f of x. This means integration is differentiation in reverse. It's the ultimate undo button for calculus. If you can differentiate a function, you already have a big clue about how to integrate its derivative. This is the most important concept to grasp. Now, let's connect this idea to the notation we use. The integral of f prime of x with respect to x is equal to f of x. The symbol on the left is called the integral sign, and f prime of x is called the integrand. The dx at the end is crucial. It tells us which variable we are integrating with respect to. Without it, the notation is incomplete and ambiguous. But there's one small but incredibly important detail to consider. Let's look at an example. What is the derivative of x squared? The answer is 2x. What about the derivative of x squared plus 5? That's also 2x. And the derivative of x squared minus 1,000? Still 2x. Do you notice a pattern here? The derivative of any constant is 0. So when we reverse this process, we can't be sure if there was an original constant or not. It vanished when we took the derivative. To account for this uncertainty, we add a constant of integration, which we represent with the letter c. This plus c is non-negotiable for what we call indefinite integrals. If you forget it, your answer is only a partial solution, because you're missing an entire family of possible original functions. So we've now understood that integration is the process of reversing differentiation, and why we need that plus c. We have achieved our first objective. Now that we understand the core concept, let's look at the basic tools we have. In this next section, you will be able to apply the power rule, constant rule, and sum rule of integration to find the integrals of polynomials. We'll start with the most fundamental rule, the power rule. Remember the power rule for differentiation? You brought the power down and subtracted 1 from it. The integration power rule is the exact opposite. You add 1 to the power and then divide by that new power. Let's see this in action. Consider the integral of x cubed. Here, n equals 3. So we add 1 to the exponent to get 4, and we divide by 4. Don't forget the plus c. The integral is 1/4 x to the 4th plus c. We can always check our answer by differentiating. The derivative of 1/4 x to the 4th is 1/4 times 4x cubed, which simplifies to x cubed. It works perfectly. What if we have a constant multiplying our function? That brings us to the constant rule. Just like with differentiation, you can pull any constant multiplier outside of the integral. You integrate the function and then multiply by the constant at the very end. For example, let's integrate 5 times x squared. We can pull the 5 out. Then we integrate x squared using the power rule. The integral of x squared is x cubed over 3. Finally, we multiply our result by the 5 we pulled out to get 5/3 x cubed plus c. Notice the constant of integration, c, is added only at the very final step, after we've performed all the integration. Finally, for functions made of several terms added or subtracted together, we have the sum rule. The sum rule is exactly what you'd expect. The integral of a sum is the sum of the integrals. This means we can integrate each term of a polynomial separately and then add the results together. Let's combine all these rules into one polynomial example. Let's find the integral of 4x cubed minus 6 plus 2. First, we can use the sum rule to split it up into 3 separate integrals. Now, we'll apply the constant rule to pull out any numbers. We have 4 times the integral of x cubed minus 6 times the integral of x plus 2 times the integral of 1. Time to integrate each term using the power rule. Remember, x is x to the power of 1. Putting it all together, our final answer is x to the 4th minus 3x squared plus 2x plus c. Again, the c goes at the very end. Great work! We've successfully integrated a polynomial using our basic rules. You are now able to apply the power, constant, and sum rules, fulfilling our second objective. So far, our integrals have looked a lot like the derivatives we learned to do. But what happens with more complicated functions, like composite functions? That's where we need a new technique called U-substitution. The goal of this section is to teach you how to recognize and solve integrals using the U-substitution method. This is the most important technique in all of integral calculus. U-substitution is the integration technique that undoes the chain rule. Let's recall the chain rule. The derivative of a composite function is the derivative of the outer function with respect to the inner function, times the derivative of the inner function with respect to x. When we look at an integral that needs U-substitution, we are looking for a function and its derivative. More specifically, we're looking for a function and its derivative hiding inside of it. Let's use an analogy. Imagine you have a set of nested Russian dolls. The whole doll is our integral. We need to simplify it by getting rid of the inner doll. U-substitution is our method to do this. The key is to identify the inside function, which is often in parentheses, under a radical or in the exponent. Let's look at this example. The integral of 2x times the quantity x squared plus 1 to the 5th power. If we tried to expand this, it would be a huge amount of algebra. There has to be a simpler way. Here, the inner function is clearly x squared plus 1. This is our candidate for u. Let's make that substitution. Let u equal x squared plus 1. Now we can't have an integral with u and x. We need to replace everything with u. To do that, we need to find the derivative of u with respect to x or du. The derivative of u du dx is the derivative of x squared plus 1, which is 2x. A common shorthand is to multiply by dx, giving us du equals 2x dx. This is a powerful step. This is the magic moment. Look at our original integral. Do we see 2x dx anywhere? Absolutely. It's right there. We found the other piece of the chain rule. Now we can substitute. Our integral simplifies to the integral of u to the 5th with respect to u. See how much simpler this looks? We've successfully broken apart the nested dolls. We can integrate this using the power rule. The integral is 1/6 u to the 6th plus c. But we're not done yet. Our original problem was in terms of x, so our final answer must be 2. We must substitute x squared plus 1 back in for u. Our final answer is 1/6 times the quantity x squared plus 1 to the 6th plus c. Let's do another one to solidify this. This time, it won't be quite as perfectly set up. Consider the integral of x cubed times the quantity x to the 4th plus 3 to the 2nd power. Again, the inner function is a good candidate for u. So let u equal x to the 4th plus 3. Let u equal x4 plus 3. Now we find du. Du ex is 4x cubed, which means du equals 4x cubed dx. Let's compare this to our integral. We see an x cubed dx, but we have an extra factor of 4. Don't panic. We can algebraically manipulate du. If du equals 4x cubed dx, then 1/4 du equals x cubed dx. Now we have a perfect substitution for x cubed dx. Substituting back in, our integral becomes the integral of u squared times 1/4 du. We pull the 1/4 out, integrate u squared, and substitute back. The final answer is 1/12 times x to the 4th plus 3, cubed plus c. By identifying the inner function and its derivative, we transformed a complex integral into a simple one. That's the power of U-substitution, and we've met our objective for this section. While U-substitution can solve a vast number of problems, there are a few common integral forms that have their own special rules. Knowing these can save you a lot of time. Our objective here is to learn to recognize these common integral patterns. So, our goal is to identify and apply the integrals of e to the x, 1 over x, and the basic trigonometric functions. Let's start with the exponential function, e to the x. This one is truly unique. We know that the derivative of e to the x is just e to the x. Since integration is the reverse of differentiation, it stands to reason that the integral of e to the x is also e to the x. This is the only non-zero function in all of mathematics that is its own derivative and its own integral. This means that functions of the form e to the x are the mathematical expression of unending growth or decay. Their rate of change is proportional to their own size. The integral just tells us the total amount. Next up is the integral of 1 over x. At first glance, you might be tempted to use the power rule. If you rewrite this as the integral of x to the negative 1, the power rule would tell you to add 1 to the exponent to get x to the 0 and then divide by 0, and we can't divide by 0. So the power rule fails here. This is a special case. We need to think about differentiation. What function has a derivative of 1 over x? If you recall, the derivative of the natural logarithm of x is 1 over x. Therefore, the integral of 1 over x is the natural log of the absolute value of x plus c. Wait, why the absolute value? We add the absolute value signs to ensure that the domain of our integrated function matches the domain of the integrand. The function 1 mag is defined for all non-zero x, but the natural logarithm is only defined for positive x. By including the absolute value, our answer, natural log of the absolute value of x, is now also defined for all non-zero x, matching the original problem. This is a very important detail. Finally, let's touch on the basic trigonometric integrals. These are also direct reversals of derivative rules you've already learned. We know the derivative of sine is cosine, so the integral of cosine must be sin plus c. And what about sine? The derivative of cosine is negative sine. That means we'll need a negative sign to get rid of the extra negative. The integral of sine is negative cosine plus c. You can find many more of these in a table of integrals, but these four, e to the x, 1 over x, sine, and cosine, are among the most important ones to commit to memory. We've now achieved our objective of recognizing these common integral patterns. Up until now, we've focused on indefinite integrals, which give us a family of functions. But what if we want to find a single specific value? This brings us to definite integrals. By the end of this section, you will be able to evaluate definite integrals using the fundamental theorem of calculus. The definite integral has a remarkable connection to geometry. It represents the net area between the curve of a function and the x-axis over a specific interval. The notation looks similar, but with one key difference: the a and b written at the bottom and top of the integral sign. These are called the limits of integration, defining our interval from a to b. This integral represents the area of the shaded region. There are two important things to remember about this area. First, its net area. Area above the x-axis is counted as positive, and area below is counted as negative. Second, it's an exact area, not an approximation like Riemann sums. So how do we find this exact area without using Riemann sums? The answer is one of the most important results in mathematics: the fundamental theorem of calculus. This theorem provides a bridge between differentiation and integration, turning a geometry problem, finding area, into an algebra problem, evaluating a function at 2 points. It says that if f prime of x is our function f of x, then the definite integral of f of x from a to b is simply f of b minus f of a. Let's break this down. The process is incredibly straightforward. First, find any antiderivative of your function f of x. Let's call it f of x. You can use all the rules and techniques we've discussed so far. A key point: for definite integrals, we don't need to write the plus c. It would cancel out anyway. Second, we use a new notation with a bracket to show we are evaluating f of x at the upper limit b and the lower limit a. This just means f of b minus f of a. Let's try an example. We want to find the area under the parabola y equals x squared from x equals 1 to x equals 3. This is the definite integral of x squared from 1 to 3. Step 1. Find the antiderivative of x squared. Using the power rule, that's 1/3 x cubed. So, our f of x is 1/3 x cubed. Notice, no plus c. Step 2, evaluate f of 3 minus f of 1. We plug in 3 to get 27 over 3, and we plug in 1 to get 1 over 3. 9 minus 1/3 gives us our final answer of 8 2/3. This is the exact area under the curve y equals x squared from x equals 1 to x equals 3. Let's do one more, a slightly more complex one. We want to find the integral of 1 over x squared plus 1 from -1 to 1. This is a very special form. Step 1, find the antiderivative. What function has a derivative of 1 over x squared plus 1? That's right, it's the inverse tangent, or arctan of x. If you don't recognize this on sight, that's okay, but it's another one worth memorizing. So our f of x is arctan of x. Step 2, evaluate arctan of 1 minus arctan of -1. The arctan of 1 is the angle whose tangent is 1, which is pi over 4. The arctan of -1 is negative pi over 4. So we have pi over 4 minus negative pi over 4, which gives us a final answer of pi over 2. Using the fundamental theorem of calculus is a powerful and elegant way to calculate exact areas under curves. We have now seen how to use the FTC to evaluate definite integrals, completing our objective. Let's put everything we've learned together. In this final section, we'll walk through a few worked examples, from a straightforward one to a more complex one, to reinforce these concepts. You will be able to solve various types of integration problems and identify common mistakes. Our goal is to practice our skills and look out for common pitfalls. Let's start with a classic U-substitution problem. Here we have the integral of x cubed times e to the power of x to the fourth. When you see e to a power, a common strategy is to let u be that power. So let's set u equal to x to the fourth. Next, we find the differential du. The derivative of u with respect to x is 4x cubed, so du equals 4x cubed dt. Now we compare this to our integral. We have x cubed dx, but we're missing the 4. No problem, we can solve for it. This gives us x cubed dx equals 1/4 du. Let's substitute everything into our integral. X cubed dx becomes 1/4 du, and e to the x to the fourth becomes e to the u. The integral simplifies to 1/4 times the integral of e to the u. And what's the integral of e to the u? It's just e to the u. The 1/4 is a constant multiplier. So we have 1/4 e to the u plus our constant of integration. The final step is to substitute x to the fourth back in for u. Our answer is 1/4 e to the power of x to the fourth plus c. Excellent. That's a textbook U-substitution problem. Let's try a definite integral with a trigonometric function. Here's the integral of sine of 2t from 0 to pi over 2. This one also needs a U-substitution because we have an inner function 2t. Let's set u equal to 2t. The differential du is 2 dt, which means dt is 1/2 du. Now here's a common mistake, forgetting to change the limits of integration. When we switch to u, our limits must also switch to u. The lower limit was t equals 0. Plugging into u equals 2t. The new lower limit is u equals 0. The upper limit was t equals pi over 2. Plugging in, our new upper limit is u equals pi. Now we substitute everything in. The integral becomes 1/2 times the definite integral of sine of u from 0 to pi. The antiderivative of sine of u is negative cosine of u. So we need to evaluate negative cosine of u from 0 to pi. This gives us negative cosine of p minus negative cosine of 0. That's -1 plus 1, which equals 2. Half of that is our final answer of 1. Because we changed the limits, we don't need to substitute back to t. Let's finish with a more challenging indefinite integral. Find the integral of tangent squared of x times secant squared of x. This doesn't look like our other examples. Let's think. Do we see a function and its derivative? What is the derivative of tangent of x? It's secant squared of x. It's right there in our integral. This means we should set a equal to tangent of x. Let u be tan of x. Then du is secant squared of x dx. The substitution is perfect. Our integral simplifies to the integral of u squared du. This is just the power rule. The integral is 1/3 u cubed plus c. Substituting back for u, our final answer is 1/3 tangent cubed of x plus c. That was a great challenge that showed the importance of recognizing derivative pairs. We've now worked through several examples fulfilling our final objective. Let's recap what we've learned today. We started by discarding the idea of integration as a memory game and instead embraced the fundamental concept. We learned that integration is the process of reversing differentiation. It's how we find a function when we are only given its rate of change. This antiderivative process leads us to the indefinite integral. Crucially, we must always add the constant of integration, plus c, to represent the family of functions whose derivative is the original integrand. This is a non-negotiable rule for indefinite integrals. For more complex integrals, U-substitution is our most powerful tool. It allows us to simplify an integral by identifying an inner function and its derivative, making a variable substitution to turn it into a simpler problem. We also learned about definite integrals, which represent the net area under a curve over a specific interval. The fundamental theorem of calculus gives us an elegant way to solve these by finding the antiderivative and evaluating it at the limits of integration. Let's quickly revisit the 3 most common mistakes students make. If you can avoid these, you're already ahead of the game. First and foremost, forgetting the plus c on indefinite integrals. It's a foundational requirement. Don't forget it. Second, when doing U-substitution on definite integrals, you must change the limits of integration to match your new variable u. And third, be careful with the power rule. Make sure you're adding 1 to the exponent, not subtracting, and dividing by the new exponent, not multiplying. Also, remember the special cases for e to the x and 1 over x. Integration is a skill that gets better with practice. Instead of memorizing, focus on understanding these core principles. When you see an integral, don't ask yourself, what formula do I use? Instead, ask yourself, what differentiation rule is being reversed here? Or, what function and its derivative do I see hiding inside? Thank you for watching. I hope this video has given you a clearer picture of how integration actually works. Keep practicing, and you'll master it in no time.